All right, welcome to Tolleson Physics. So what we're going to look at today is an elastic collision between two objects. And so an elastic collision is when two objects basically bounce off of each other. There's some energy considerations that we'll add to that when we talk about energy and more, but momentum is conserved in this case. And this is a closed system. And so when we look at what we're going to do is I'm going to have this block go towards, so block of 1m is going to go towards a block that's triple that amount. And so I'm going to send it into that block at 10 meters per second, and this other block is stationary. So when this block hits that, since it's a lower mass, it's actually going to bounce backwards. And we can determine that. So we measured that as negative 5 meters per second. So its speed looks like it's cut in half, interestingly. So what happens to the 3m? So that's the question that we have today. So we're going to use conservation of momentum. So the initial momentum equals the final momentum. Now, I didn't include the impulse in this particular example because there's no external forces. We're going to assume that the surface of this is frictionless, and we're just going to see what happens in a frictionless environment. So what does that mean? So before I put in numbers, let's actually talk about what this all means. So let's call this A and call this B so we can keep track of it. That's a funny looking B. And so what's going on with the momentum beforehand? Well, I have my mass of A going at an initial velocity for A. B's not moving, so anything times 0 is 0, so I won't include that. But then I have the mass of A traveling at a final velocity plus the mass of B at a separate final velocity. And this is what we want to figure out. All right, so we could solve for that, but I think what I'm going to do in this particular case is let's put in numbers and figure out what's going on. And so the mass was 1 mass unit times 10 meters per second. And that's going to equal 1 mass unit. And then I do need to know this. There's a way to figure this out after we get to energy. So I'm going to give you one of these. And so it's going backwards, other direction at 5 meters per second. So that negative sign is going to be important. So I'm going to consider going to the right positive in this particular case. So what I need to figure out, so the mass is 3 mass units for B. And I want to know that final amount. All right, so we can do that. So I have the masses actually cancel, right? There's an M, an M, and an M. So that kind of goes bye-bye, thankfully, right? So that cancels out. And so what am I left with? This is 10 meters per second equals negative 5 meters per second plus 3 times VF for the B block. And so then I need to add 5 to both sides. So I get 15 meters per second equals 3 final velocity of B. And so finally that final velocity of B looks like it's 5 meters per second in the other direction. So just happened to pick numbers that it ended up being the same speed in both directions. That was unintentional, but it's the way it worked out. And so we can see what is going, we can use conservation of momentum to predict, if we have enough information, to be able to predict what the velocity of that's going to be. Another type of question I could ask instead is, well, maybe we measure both velocities and one of these is an unknown mass unit. We could solve for the mass instead. So we're using conservation of momentum. This is a closed system, so there are no external forces, so we can simply say that the initial momentum equals the final momentum. All right, the only way to do physics is to practice physics. And so here's the problem from our video. We had the light mass block hit a heavy mass block. So go ahead, solve it without looking back at the video, hit pause, and then when you're ready, unpause to see the solution. All right, here's the solution that we went through in the video. You can always go back to the video to see what was done. Now, here's a different situation. So once again, we switch the masses so the more massive block is now going to hit the less massive block. So let's see how that changes it. Note that the more massive block in this case doesn't bounce backwards, it actually keeps going forward at 5 meters per second. So hit pause and predict what the velocity of mass m will be. All right, here's the solution for what happens. The block with mass m travels to the right at 15 meters per second. So keep practicing, and we'll see you next time.